Welcome back to the Code Navigators. Our goal here is pretty simple, really.
It is. We want to chart a course chapter by chapter through the sometimes very dense landscape of the International Code Council code books.
Exactly. We want to make these complex documents a little more manageable, a little more memorable for you.
Right. We're here to give you the context and the really critical details that help you not just for exams, but to be a better professional.
And as we do that, we want to be totally transparent about how this works. The script generation is AI assisted.
But, and this is a big but, it's all under the production and really the oversight of a human code professional. We're just using the tech to help us organize this for you.
Okay, before we jump into today's topic, we have to start with our legal disclaimer. It's mandatory.
And absolutely critical. So please know, this discussion is purely for educational and informational purposes. That's it.
We really need to emphasize this. This is not professional advice. You can't use this as a substitute for talking to a qualified code official or a design professional for your specific project.
Never. Codes change, local amendments are a big deal, and every project is unique. We're looking at the IBC 2021 Model Code.
So you always have to consult the official current code for your area.
And a final point, we're analyzing the code's structure and intent. We're not stating any copyrighted material verbatim. We're just discussing what it means.
Right. With that very necessary foundation laid, let's get into it.
Let's do it. Today, we're tackling a big one.
Oh.
IBC 2021, Chapter 21, Masonry.
Masonry. I mean, this is one of the oldest building systems we have, right? Bricks, blocks, mortar. So what's the big picture mission of this chapter?
It's really comprehensive. Section 2101 basically tells us its job is to set the minimum requirements for everything to do with masonry.
Everything. I mean, everything.
Material specs, the different design methods, plain versus reinforced, how you actually build it, the quality assurance.
And it even gets into things like fireplaces and chimneys, right?
It does. Fireplaces, chimneys, masonry heaters. It's a huge scope, all aimed at, structural integrity and making sure the stuff lasts.
Okay, so for someone studying this, or maybe a professional on a job site, what's the one piece of advice for navigating Chapter 21 without getting lost?
The single most important thing to get is that this chapter heavily relies on other documents. It outsources the deep technical details.
So the IBC itself doesn't have all the answers.
Not at all. You have to get comfortable with cross-referencing, especially to the TMS standards. That's the Masonry Society. You'll see TMS 402 and TMS 602 referenced constantly.
And what are those?
TMS 402 is about structural design, and TMS 602 is about the specs for materials and construction. If you try to study Chapter 21 by itself, you're only getting like half the story.
So the IDC sets the rules, and the TMS tells you how to follow them, technically speaking.
That's a great way to put it. The IBC sets the performance bar, and TMS gives the engineer the how-to.
Okay, that makes sense. Let's start unpacking it then. We'll start at the beginning with the fundamentals in sections 2101 and 2102.
The scope and the language. Let's do it.
So section 2101.1 lays it out pretty clearly: materials, design, construction, durability. But then 2101.2 immediately throws you into that cross-referencing you mentioned.
Yep. Right away, it tells you your design has to follow TMS 4022602 or maybe TMS 48603 for some other systems.
Why do they do that? Why not just put the rules in the IBC?
Well, masonry engineering is a really specialized field. The science is always evolving. So instead of the ICC rewriting highly technical formulas every 3 years, they just defer to consensus standards from the experts at the Masonry Society. It keeps the IBC from becoming a 10,000-page book.
And it keeps engineers using the most current methods.
Exactly.
Okay, that brings us to section 2102, the symbols and notations. This feels like the part everyone skips.
It's so easy to skip. You see a list of symbols and think, I'll figure it out from context. But that's a huge mistake.
Why is it so critical?
Because it's literally the dictionary for all the structural parts of the chapter. Without it, the formulas are just, alphabet soup. You have to know what F'(M) stands for. It's the absolute prerequisite for doing any kind of calculation.
Let's talk about a few of those. You've got D sub B, which is just the diameter of the rebar. Simple enough.
Simple, but it drives a lot of other calculations like lap lengths. And you have F subs, the allowable stress in the steel. Standard stuff.
But you mentioned F'(M). You said that's the big one.
It is. If you take one thing away about structural masonry, it's F'(M). It stands for the specified compressive strength of the masonry assembly at 28 days.
Okay, let's break that down. Why the whole assembly and why 28 days?
It's critical because it's a performance spec, not a material spec. It's not the strength of the block by itself or the mortar by itself.
It's all of it working together.
It's the whole system. The block, the mortar, the grout, the rebar, all working as one unit. When an engineer puts on the drawings that F'(M) needs to be 1500 psi, they're talking about the final strength of the wall you actually built.
And the 28 days.
That's all about the chemistry of cement. It takes about that long for the cement in the mortar and grout to cure and reach its intended design strength. Testing at 28 days is the industry standard to verify that what was built meets what was designed.
So that symbol, F'(M), really connects everything, the materials, the construction quality, and the engineering design.
It's the linchpin. And you'll see other symbols in 2102 that relate to the testing itself, like P for the applied load, and S sub P and S sub W for the dimensions of the test specimen. It's all part of that verification process.
So, pro tip for studying. Start with 2102. Learn the language before you try to read the book.
100%.
All right, if 2102 is the language, section 2103 is the list of ingredients, right? The materials we're allowed to use.
That's a perfect analogy. Section 2103.1 lists them out. Concrete block, clay brick, stone, glass block, AAC masonry.
And the key thing here is that every single one has to conform to a specific ASTM standard.
Right. You can't just go buy any concrete block.
Yeah.
It has to meet ASTM C90, for example.
And that standard dictates things like its minimum strength, how much water it can absorb, its dimensions.
Exactly. It provides consistency. An engineer anywhere in the country knows what they're getting with a C90 block. It removes the guesswork.
There's an interesting exception in there for structural clay tile.
Yeah. It notes that if the tile is non-structural, so it's just for looks, not carrying a load, it doesn't need to have a fire resistance rating.
But it's not a total free pass.
No, not at all. It still has to meet the compressive strength standards. The code just wants to make sure it won't, crumble under its own weight or from minor building movement.
That makes sense. Quality still matters. Now, what about something you see a lot in renovations? Using secondhand units. Section 2103.1.1.
This is where the code gets very practical. You can reuse units, which is great, but there are strict rules. They have to meet the standards for new units, be free of cracks, and this is the big one. All the old mortar has to be cleaned off completely.
Why is cleaning off the old mortar so important?
It's all about the bond. New mortar needs a clean, porous surface to stick to. If you leave old hard mortar on there, the new mortar just kind of sticks to the old mortar, creating a weak spot right in the joint. It completely undermines your F'.
Right, you'd never get the strength you designed for.
Never.
Okay, let's move on to the glue that holds it all together. Section 2103.2 and 2103.3 mortar, grout, and adhesives.
The basics for mortar and grout, again, are referenced out to TMS 602, but the IBC calls out some specialty stuff, like surface bonding mortar and specific mortars for porcelain tile.
And there's a really useful table in there, table 2103.2.3 for ceramic tile mortar.
That table is like a recipe book for installers. It tells you the exact mix, how many parts cement, lime, and sand for different uses. A scratch code is different from a wall-setting bed. It takes the guesswork out of mixing on site.
It's very prescriptive.
Very. It's designed to prevent errors.
Then there's a quick mention of organic adhesives, type 1 adhesives. In section 2103.2.6, they have a surprisingly low strength requirement.
They do. We're talking less than 50 psi as of shear strength, and it drops to under 40 psi if it gets wet. The code does this on purpose.
Why so low?
Because these aren't for structural use. They're for, say, sticking tile on a wall in a dry area. The low limit ensures they're not accidentally used where their failure could cause a structural problem. The code is basically saying this stuff is not for holding heavy things up.
Got it. And finally in the section, we get to the steel reinforcement in 2103.4.
The backbone. All the rebar and accessories have to meet ASTM A706. This ensures it has the right strength and, just as important, the right ductility to bend without breaking, especially for seismic performance.
And if you want to use some new, non-standard reinforcement,
you can't. Not until you've had it tested and proven to the building official that it performs just as well. It's a high bar to clear.
Okay, that covers the ingredients. But having the right ingredients doesn't guarantee a good meal. You need quality control.
That's the perfect lead-in to Section 2105, Quality Assurance.
It's the check system.
It is. It's the bridge between the material science we just talked about and the design performance we need to achieve. It says all masonry construction needs a QA program that follows Chapter 17 and TMS 602.
Which means inspections, testing, documentation.
All of it. It's how you verify in the field that the wall is being built right, so it will actually achieve the F' the engineer called for.
Makes sense. Now, section 2106, seismic design, again, the code immediately points you somewhere else.
Right to Chapter 7 of TMS 402. And for good reason. How masonry behaves in an earthquake is incredibly complex. It depends on tiny details, reinforcement spacing, how things are connected. So the IBC defers to the highly specialized, constantly updated rules from the experts.
Okay, now for the two big engineering philosophies in the code. Strength design in section 2108 and allowable stress design in section 2107. What's the difference, conceptually?
It's a core concept in engineering. Think of allowable stress design, or ASD, as the more traditional, cautious method.
How so?
With ASD, you figure out the ultimate strength of your material, and then you divide it by a big factor of safety, like 2 or 3. The number you get is your allowable stress, and you design the structure to make sure the stresses from everyday loads never ever exceed that low number.
So you're factoring down the material's strength to create a safety buffer.
Exactly. Now, strength design, or LRFD, flips that around. Instead of factoring the material strength down, you factor the loads up.
So you take the expected loads from people, snow, wind, and you multiply them by factors bigger than 1, creating a sort of worst-case scenario load.
Precisely. You design the structure to handle that hypothetical, beefed-up load. It's a different way of thinking about safety, and it often lets you use materials more efficiently, but it requires a more sophisticated analysis.
And both are allowed by the code.
Both are perfectly acceptable.
Within both of those methods, connecting reinforcement bars is critical. Let's talk about lap splices.
A lap splice is just where you overlap 2 pieces of rebar to transfer the force from one to the other. The length of that overlap, called L sub d, is determined by a calculation in equation 21:1.
We don't need to do the math here, but what are the basic rules for that length? Are there minimums and maximums?
There are. No matter what the formula says, the lap can't be less than 12 inches, and it can't be more than 40 times the bar diameter. It's a practical range to ensure the splice works without creating too much congestion.
What about other connections, like mechanical or welded splices?
The code gets specific there too. Mechanical splices are broken down into type 1, type 2, and type 4 based on how strong they are.
And I hear there's a big restriction on type 2 splices.
A very important one. You can't use a type 2 splice anywhere you need the rebar to develop its full tensile strength.
Which means what in the real world?
It means you're forbidden from using them in the most critical parts of a structure in an earthquake zone. Places like a plastic hinge zone.
A plastic hinge zone. What is that?
Think of it as a designated weak spot, an area in a beam or column that's designed to bend and yield during a major earthquake. It's like a seismic fuse that absorbs energy.
So it's supposed to get damaged to save the rest of the building.
Exactly. And because that area is going to be stressed to its absolute limit, any splice in there has to be as strong as the bar itself. A type 2 splice isn't, so it's not allowed. You need a type 1. It's a critical life safety detail.
That makes perfect sense. Okay, let's switch gears to some of the more specialized, prescriptive types of masonry. We'll start with empirical design in section 2109.
Empirical design is basically the cookbook method. It's based on time-tested rules of thumb like, for a wall this high, it needs to be this thick. You don't do complex engineering calculations.
But the code puts some pretty tight limits on where you can use it.
Oh, yeah. It's really only for simple low-risk buildings, generally 1-story max. If you have complex loads or you're in a high seismic area, you can't use it. You have to do the full engineering design.
Now, what about something really specialized, like adobe masonry? Section 2109.2.
This is a fascinating material. It's basically dried mud brick, so the testing is totally different from concrete block. The code has 2 key strength requirements.
Okay, what are they?
First, it has to have an average compressive strength of at least 300 psi. Not a lot compared to concrete, but essential for carrying vertical load.
And the second one?
The second is the modulus of rupture. It has to be at least 50 psi. This tests its ability to bend a little without snapping. For a brittle material like adobe, this is a really important measure of its quality and durability.
The rules for wall thickness are also very specific.
They have to be. Because the material is weaker, you need more of it. A non-load-bearing exterior wall has to be 10 inches thick, minimum. A load-bearing wall has to be 10 inches plus 1/10 of its height. They're very thick walls.
And they require something called a tie beam.
A tie beam is essential for adobe. It's a continuous beam, either concrete or wood, that runs along the top of the walls, literally tying them all together into a rigid box. Without it, the walls could just peel apart at the corners.
There's also a great practical table in there, table 209.2.3, about the strength of bolts in adobe.
This is your cheat sheet for installations. It tells you, for example, that if you're bolting a wood sill plate down, a 1/2-inch bolt needs to be embedded at least 12 inches deep to get 200 pounds of shear strength. It's a non-negotiable detail for connecting the roof to the walls.
All right, let's make a hard turn into life safety. Masonry fireplaces, section 2111. The rules here get incredibly specific.
As they should. Fire is unforgiving. It starts with the foundation, the footings. They have to be solid concrete, at least 12 inches deep and below the frost line. You can't have a massive, heavy fireplace settling and cracking.
What about the firebox itself, the walls?
At least 8 inches of solid masonry or concrete. Or you can use a thinner structural wall if you line the inside with fire brick. The fire brick takes the brunt of the heat and protects the structure behind it.
Let's talk about the hearth extension, that non-combustible area on the floor in front of the fireplace. The dimensions are very precise.
They are, and it's all about preventing fires from rolling logs or shooting embers. The hearth has to be at least 4 inches thick. For a small fireplace opening, it needs to stick out 16 inches in the front and 8 inches to the sides.
16 and 8 for a small one.
Right, but for a large opening, 6 square feet or more, the risk is greater, so the dimensions go up to 20 inches in front and 12 inches to the sides.
20 and 12, got it. Now, probably the most common mistake an inspector finds. Clearances to combustibles, section 2111.13.
This is so important. You have to think about 2 different kinds of heat. First is conducted heat.
The heat that travels through the masonry.
Exactly. To deal with that, you need a 2-inch air gap between the outside of the masonry fireplace or chimney and any wood framing. That air gap is a thermal break.
2 inches for conducted heat? What about the heat coming out of the front opening?
That's radiant heat, and it's much more intense. So for that, any combustible material like a wood mantle or trim has to be kept at least 6 inches away from the opening.
So 2 inches around the back and sides, 6 inches around the front.
That's the rule. It's simple, but it saves houses from burning down.
Okay, moving up from the fireplace to the masonry chimney in section 2113.
The rules continue. The chimney walls themselves have to be at least 4 inches thick of solid masonry.
And they must have a flue lining, right?
Mandatory. You have to have a clay or cast-in-place liner. It does 2 things. It contains the intense heat, and it protects the masonry from the acidic moisture and the smoke, which can eat away at the mortar over time.
Then there's the famous chimney height rule, the 3-2-10 rule.
The 3 feet above, 2 feet from 10 rule. It's critical. The chimney has to terminate at least 3 feet above the roof where it pokes through, and it has to be at least 2 feet higher than anything within a 10-foot horizontal radius.
Why is that so important?
2 reasons. It prevents wind from blowing down the chimney and pushing smoke back into the house. And more importantly, it gets the sparks and embers up and away from the roof so they don't set it on fire.
And finally, you can't just guess the size of the flue.
No, flue sizing is an engineering calculation based on the fireplace opening size and the chimney height. There are tables and figures in the code to guide you. Too small, and smoke comes in the house. Too big, and you don't get a good draft. It has to be just right.
Okay, one last system to cover before we wrap up. Dry stack masonry in section 2114. This is totally different. No mortar in the joints.
Right. With dry stack, you use these precision-made interlocking blocks, you stack them dry, and then you basically plaster both faces with a surface bonding cement, which is a fiberglass reinforced mix.
Why would someone use this method? It sounds less robust.
It can be faster and requires less skilled labor than traditional masonry, but you're right, there is a big trade-off in terms of structural strength.
Which leads to the code's single biggest restriction on it.
The absolute deal breaker. Dry stack masonry is flat out prohibited in structures in seismic design category 4, the highest risk seismic zones.
It just can't handle the shaking.
It can't. The system relies on a thin surface coating for its sheer strength, which is just not reliable enough for the kind of forces you see in a major earthquake.
And even where it is allowed, the material standards are still there.
Oh yes, you have to use ASTM C90 units, and the allowable stresses are incredibly low. You can see them at table 2114.4.
How low are we talking?
The maximum compression allowed is only 45 CI. Compare that to the 1500 CSI or more we talked about for engineered masonry. It's really only for low-stress, low-risk applications.
It's a great example of the code allowing for different methods, but drawing a very hard line when it comes to life safety.
It's the ultimate safety filter. You can do this, but not here.
Well, that brings us to the end of our journey through IBC 2021, Chapter 21. A lot to cover there.
A ton. But I think we navigated the big points. The materials, the engineering frameworks, and all those prescriptive safety rules.
So to recap for everyone, what are the key takeaways?
I'd say there are 3. First, master the material specs. Know that everything has to tie back to an ASTM standard.
Second, understand the difference between the two main design methods, allowable stress and strength design, and know that the real engineering details are in TMS 402 and 602.
And third, memorize those life safety rules for fireplaces and chimneys. The
Yep.
2-inch clearance, the 6-inch clearance, the 3-2-10 rule, those are non-negotiable.
And through it all, remember that key variable.
Of prime VIM, the specified compressive strength of the whole assembly at 28 days. It's the performance metric that ties it all together.
Okay, so to wrap this all up, we want to leave you with a final thought to connect all these ideas.
We talked about material science on one hand, the ASTM standards, and structural engineering on the other, the F prime calculations. They can seem like two separate worlds.
So here's the question to think about. How does the quality assurance program, the thing from Section 2105, act as the bridge between those two worlds?
Right. Think about it. The QA program isn't just about filling out forms. It's the actual on-site process that verifies that the materials the engineer assumed you would use are being installed correctly to achieve the strength the design relies on.
Without that bridge, the engineer's design is just a theory.
It's just a prayer. Quality assurance is what makes structural safety a reality in the field. It's something to really mull over.
A great final thought. And if you found this discussion helpful for your studies or your work, you can help support our program and help us make more content like this.
Just visit the Patreon link you'll find in the show description. Any support is hugely appreciated and helps us keep doing this.
Thank you for navigating this chapter with us.
Until the next one, keep studying and keep building safely.
We'll see you next time on the Code Navigators.